So we're going to do a whole chapter on the periodic table later, but for now there's just a few things that you need to know. One is that it's organized by increasing atomic number, and just to review, we said atomic number was the number of protons, which identifies the element. If I ever say the word period, I'm talking about a horizontal row, so that would be left to right. And if I ever refer to a group or a family, I'm talking about a vertical up and down column. And just so you can remember, if I ever say family, think of family tree. Trees grow up and down. That'll help you remember it. Up until now, we've just talked about the atom in terms of the nucleus. We have the nucleus in the middle and the electrons floating around the outside. Bohr, B-O-H-R, is the first scientist who understood that electrons are arranged in regions around the nucleus, and he called those regions energy levels. So they look kind of like the planets floating around the sun, and that's why we call it the planetary model. So if you can remember that Bohr did the planetary model, just picture it like a solar system with the nucleus in the middle and the electrons in rings around that positive nucleus. And what Bohr did is he used experiments on hydrogen to develop this model. What he figured out is that the electrons circle the nucleus only in fixed energy levels, and remember, energy levels are the rings around the nucleus, so it's like an orbit. An electron can neither gain or lose energy within the orbit, but it can move up and down to different orbits. So we're going to talk about how an electron can jump to different orbits in just a minute. Keep in mind that the closer you are to the nucleus, the lower the energy is going to be. Chemistry joke of the day. Most people would just think they spelled boring wrong, but it's actually referring to the scientist. So energy levels is an important word. These are the regions of space where the electrons exist. And because that's hard to remember, what I want you to think of is the word rings. When you hear the words energy levels, the word rings needs to pop into your head, because that'll tell you that it's the rings around the nucleus where the electrons are. When the electrons are all arranged so that they're as close as they can possibly get to the nucleus, we call it the ground state. So for example, if you have two electrons and they're both in that first energy level, that's called the ground state. Excited state is if you give them a packet of energy called a quantum. You can move the electron to a higher energy level. So if you have those two electrons in the first energy level and you give them energy, you can make them jump to the second energy level. However, that state is very unstable, so it won't stay like that for very long. So a few things about Bohr's model. If you think of it like a circular ladder, it takes energy to climb up the ladder, so you have to give energy to an electron to make it move to an outer energy level. So the lower they are, the closer they are to the nucleus. The higher you go, the more energy it takes to get it to move to that farther energy level, and the more unstable it is. So if you have an electron go from the first energy level to the fifth, that would take a ton of energy to make it jump out that far, and it would be very unstable, so it wouldn't stay that way very long. And just notice the rings get a little bit closer together as you move out. That's going to be something we'll talk about a little bit later. So an emission spectrum is what we produced in class with the Flame Lab. And the way we did it is that the electrons all started in the ground state. So when they're sitting on the counter, all the electrons are as close as possible to that nucleus. They can gain energy, and what we did in class is we put them into a flame, and the flame gave the electrons enough energy to move away from the nucleus, and we call that the excited state. But because the excited state is unstable, it returns back to ground state, and in the process it has to release the energy that it received from the flame, and that energy is called an emission spectrum. So when you saw the flame turn colors, those colors were produced as the electrons moved from the outside back to the inside. And the biggest mistake I see people make here is they tell me that they see colors, they see the emission spectrum when the electrons gain energy, and that's the exact opposite. You see the spectrum when the electrons lose the energy that they already gained. So it's as they go from excited to ground state. So here's the definition of emission spectrum. It's kind of a long one. It's when the electrons move to a lower energy level, and it releases an amount of energy equal to the energy difference in those levels. It's kind of a long definition. Just make sure that you understand that it goes from the excited state to the ground state. And the emission spectrum is given off as radiation. And in the lab that we did, there were photons, which are packets of light. So when you see photons, think light. So this is what we did in the lab, and you should have been able to see the different colored flames. Keep in mind that no two elements have the same colors, the same set of colors, because they all have different sets of electrons. And the farther the electron falls, the greater the amount of energy is released. And this is the exact science behind what we do in the real world when we light fireworks. So the fireworks that you see are actually electrons that have been excited and are falling back down to the ground state. And as they fall back down to ground state, they're releasing that energy that they gained. And scientists or pyrotechnicians, they can choose the colors they want based on the chemicals, because each element has its own color. And at this point, you'll need to take out your reference tables. And you want to turn to the page that has the target. It looks like the Bohr model. Looks like a target. It is the Bohr model. And those dots are going to represent electrons. So as the dots move down towards the nucleus, they're changing energy levels. So if you look at the dot, we're on the target page, look at the dot that's at 3 o'clock, if it was a clock. That first dot you get to as you go over to the right. Notice that it starts on the 4th energy level, and it ends on the 1st energy level. Anytime an electron makes that transition, it always gives off the same amount of energy. So if you follow that dot all the way down, you should get to the number 97. Look at the number 97. That talks about the wavelength, and the type of radiation given off is even below that. It's called ultraviolet, the UV. So the first question on this slide says, how much energy is released when an electron moves from the 3rd energy level to the 1st energy level? So the first thing is you want to find the dot that starts on 3 and ends on 1. And it should be the dot right next to the one that we just did. If you follow that line all the way down, you get to 103. So that's the wavelength, and the type of radiation is still ultraviolet. Number 2 says what color light is released when an electron goes from 4 to 2. So first you have to find the dot that starts on 4 and ends on 2. So start on the 4 and circle it around, and you should find a dot that goes from 4 to 2 and has a wavelength of 486. So find 486. That should be the dot that goes from 4 to 2. What you're going to do is take that number, 486, and bring it all the way down to the bottom of that page, and you should see a visible light range that goes from red to violet. You just need to find where 486 fits into that range. And the problem is they have the numbers written in scientific notation. These are actually in nanometers, and they have these measured in meters. So the decimals are going to be a little bit off. So if you notice that the visible light range goes from 4 to 7, you have 486, just bump the decimal until it fits into that range. So if you make it 4.86, it'll fit between 4 and 7. And 4.86 falls directly in the blue range because it's between 4.2 and 4.9. So the answer to number 2 is blue. Number 3 says what wavelength would be given off if you see red light. So if you look down at the colors at the bottom, notice how red goes from 6.5 to 7. So if you go back up to your target picture, you need a number that starts with either 6 or 7. And the only option there is 656 in the visible range. And you can see that that's from energy level 3 to 2. So the wavelength that could be given off is 656. There's a worksheet in your packet, worksheet number 4. So if you're having trouble with this, try some on worksheet number 4 and you can check them in class. Electromagnetic radiation is basically just energy that has both electric and magnetic properties. And all of these types of radiation travel through empty space at the same speed. We call it the speed of light. One quick thing is about electrons as we're talking about these. Electrons can actually act like particles or waves. And what I mean by that is that they have properties of particles, where if you think of a particle, they react like a particle. But they also have properties of waves like wavelength and frequency. So it's kind of hard to wrap your head around that idea. Just keep in mind that electrons can act like a wave or a particle. And some properties of waves that we need to talk about are frequency, wavelength, and energy. Wavelength is the distance from one peak to the next. Frequency is how many peaks pass by one point in a second. So if you put your finger out and you counted how many peaks passed by your finger in 1 second, that's what frequency is. Crest is the top of the wave and trough is the bottom. You used to have to know how to do calculations with wavelength, frequency, and energy, and that's all been taken out of the curriculum. So all you really need to know now is the relationship between them. So if you look at these two waves, notice how the one on the left has a short wavelength and the one on the right has a big wavelength. So if you picture these two waves moving, if you stuck your finger out and you saw which one had more peaks pass by in 1 second, you should see that the one with the shorter wavelength has more peaks that pass by, which means that the shorter the wavelength, the higher the frequency. That's an indirect relationship because as one goes down, the other one goes up. As you shorten the wavelength, the frequency would increase. Another word for that is inverse relationship. So you could see inverse or you could see indirect. When we're looking at wavelength and energy, the shorter the wavelength, the higher the energy. So again, it's an indirect or inverse relationship. But frequency and energy are directly related. So the higher the frequency, the higher the energy. If you look back at your reference tables, the electromagnetic spectrum is in the middle, and it lists these from radio waves to gamma rays. The only thing they tell you in the reference packet is about the wavelength. So they tell you that radio waves have the longest wavelength, and they tell you that gamma rays have the shortest wavelength, but they don't give you any information about frequency and energy. So you need to know the relationship. You need to know that the shorter the wavelength, the higher the frequency, and the higher the energy. And the last thing for today is about the quantum model. So Schrödinger is the one that came up with this. It's very similar to the Bohr one. The difference is that we cannot pinpoint the exact path of an electron. We only know the probability. And notice that the word probability is in bold with exclamation points. That means it's important. So because we only know the probability, we get shaded regions instead of exact circles. So the whole atom ends up looking like an electron cloud. So if you look at this picture here, notice that right next to the nucleus, it's shaded kind of a dark orange. That means that there's a high probability of having an electron there, so maybe it's 95%. As you move away from that, notice that you have a really light pink circle, and that's because the probability has dropped. So now you have a low probability of having an electron, so the shaded region gets lighter. But then as you move out again, notice that the outside circle is a dark orange again, and that's because it's a higher probability. So since we don't know exactly where the electron is, we can just plot the probability, which makes it look kind of fuzzy and shaded, and that's why we call it an electron cloud. So this is the progression, and I'm sorry that I did it in Microsoft Word, so it's or Microsoft Paint, and so it's a little bit ancient. But on the left, you see that's the original scientists. They just thought the atom was just a sphere. Rutherford discovered the nucleus, so now you've got a positive nucleus surrounded by the electrons. Bohr is the one that talked about the energy levels, and remember, energy levels are just the rings around the nucleus. So instead of thinking electrons could exist anywhere, he put them into certain rings. And the last one's kind of hard to do with Microsoft Paint, but you should have a dark shaded region followed by a light shaded region, then a dark shaded region, a light shaded region. So you still have energy levels, but they're not perfect circles. They're just fuzzy, and that's because all we know is the probability of the electron. So these pictures, sometimes pictures help a whole lot more than words, so hopefully these pictures will help you remember the progression of the atom. And that's all for today.